J.D. Pimentel.
Thank you. So, good morning, everyone. Thanks for the invitation. It's great to be here. Great to see people physically again. Right, so I am a computer systems person. So I'm going to talk about computer systems, but from the perspective of building these systems to make them better handle AI workloads, application workloads. And also very briefly, at the end of my talk, I will also look at the other side of the coin where we can use AI to make better systems, and in this case, more robust systems. Right, so let me start off. So I'll start off with talking about systems for AI. So what can we do as systems people for the AI field? Well, probably you have seen this graph before. Yeah, so the systems community has been very important for the current ongoing AI revolution. And that is depicted in this graph, where you can see that over time we have been able to train larger and larger models. And especially in the last decade, something happened, yeah, where this increase kind of exploded, yeah, and that is clearly because we introduced the accelerators, the hardware accelerators, and these were mainly the GPUs, but nowadays we also have other types of accelerators like TPUs and so on. Yeah, and now this enables us to train very complicated large neural networks. Now, I'm not going to talk about training actually. I'm going to focus on the inference of models, but more about that later. If you look at the type of computer systems that are involved in, let's say, handling AI types of workloads, or any workloads for that matter, clearly we have our general purpose systems like PCs, desktops, laptops, servers, server farms, and so on. But there are many, many more types of computer systems around. Yeah, TVs, smartwatches, mobile phones, cars, they all have microprocessors in them that are possibly involved in, let's say, doing AI workloads. And these are just a couple of examples of these type of systems. So this is, let's say, the domain where I'm going to talk about. These are what we call the embedded computer systems. So they embed microprocessors, many of them actually, as you can see in this graph. Yeah, so the market of the microprocessor market is much bigger for this particular domain than it is for the general purpose domain. Yeah, so this is a very interesting market, to be honest. So I'm going to talk about these embedded computer systems, and these systems are mostly involved in, let's say, the inference side of the AI handling, yeah, not so much in the training side. Now, if you look a little bit closer to these embedded computer systems, to design these systems, there are many, many more requirements for designing those systems when compared to the more classical or the general purpose computer systems. Clearly, they have to be performant. Yeah, many of these systems have to deal with deadlines. Yeah, think about autonomous car. They have to make decisions on time, otherwise it may crash or whatever. Yeah, very bad things may happen. Many of these embedded systems are battery operated. They do not have active cooling. So that means that they have to be power efficient or energy efficient. Furthermore, they have, let's say, restricted resources in terms of memory. Yeah, that means that the memory footprint cannot be very large for these systems. They have to be reliable, because many of these systems are mission and safety critical. Yeah, so bad things may happen if something goes wrong here. And finally, I will not talk about that much, security, clearly. Many of these embedded devices are connected, and that means that they are a target for hackers as well. Yeah, so they have to be secure. So these are all design requirements, and designing these systems, you have to somehow meet these requirements. Now, the way the field has approached this in order to design systems that can meet all these requirements is that these systems typically have a heterogeneous underlying system architecture that have different types and flavors of processing units, and that mix can give you this different trade-offs that you need. Yeah, so these systems typically integrate general purpose microprocessors, but also different types of accelerators, like GPUs, like ASICs. So these are dedicated pieces of hardware that can do something very efficiently, and so on. But these are all integrated on a single chip, usually in the field of embedded systems. And these different types of processing elements provide different trade-offs in terms of flexibility on one hand. So how flexible can you support different types of applications versus the performance, yeah? So the performance per watt, for example. Now, a very important aspect in designing these type of systems is that you have to explore all these different design decisions that you have. Yeah, which type of processors are you going to use in these systems? How many of them? How will they be interconnected, and so on? So this is something we call design space exploration. Yeah, where we need to find a system that provides the right trade-offs that you want to have. Well, I'll be coming back on this term design space exploration quite a lot in my talk. Now, to say a little bit more about this process of design space exploration. So typically this is a process that is done at design time, yeah? And for that we use all kinds of search algorithms to search the vast design space. On the right here you see an example where a genetic algorithm, for example, is being used to explore, let's say, different mappings of application tasks to underlying resources in a system. Where you have, let's say, an encoding of the task mapping into chromosomes, and you use the genetic algorithm basically to evaluate these mappings, for example, using simulation, and then you actually act on these chromosomes using genetic operators to create a new population, and so on. So you iterate on that a couple of times, and then hopefully you will end up with a good set of solutions. So this is a typical example of how people approach these kind of problems. And of course, a lot of research has been done to make this search process a lot more efficient and more effective, like introducing domain knowledge in this search process, or using AI techniques, machine learning techniques, to do very quick prediction of how good a certain implementation or solution is, instead of doing a very expensive simulation, and so on. But sometimes it's also needed to do these kind of techniques at runtime. Yeah, sometimes you also have to take runtime decisions, and there as well we sometimes apply machine learning techniques to assist us or assist the system in that. Yeah, so you can use heuristics, but you can also use, and that's more recently research that has been done, you can also use neural networks that are implemented on the system to make these runtime decisions. For example, where a certain software thread is being executed on which processing core, and so on. Now, I'm slowly moving to the core of my talk. So what we also see in this embedded domain is a shift from cloud computing towards the edge computing. Yeah, so so if you look at embedded devices that are involved in running AI workloads, typically or traditionally, I must say, this was done using cloud services, where you have edge devices like mobile phones and so on, yeah, that are communicating with the cloud. Yeah, they send the data to the cloud, and the AI model is actually running in the cloud, and after a while you'll get back your answer. I mean, we all know the series and things like that are typical examples of that. Now, there are clearly some problems with this model. Yeah, you always need connectivity with the cloud. There is a latency involved, yeah, sending and receiving the data, and there is a privacy issue. Yeah, so in some cases it's very hard to send the data to a cloud system like Meta or medicine data or something like that, health data. So what we have seen recently is a movement where we try to actually run these AI workloads at the devices, the edge devices themselves. So very close to the data that is produced by these devices. And we call that edge AI. Now, if you look at doing that kind of stuff, then actually you have to revisit the way you design these AI algorithms, these deep neural networks. And to understand that, let me take a closer look at the way that it is traditionally done. So this is a traditional flow of designing neural networks that are targeted for embedded devices. Yeah. So typically you start with a problem or data set, you design your DNN, yeah, and then you have a trained DNN. So this is the typical way of we all do it, yeah. And then there's this manual process that's going on where you manually try to port that DNN to your embedded device, yeah. And if you have multiple embedded devices, you do that manual process multiple times, basically. Now, and what typically happens is that whenever you reach this stage, then you find out it doesn't fit. Yeah, I mean you don't have the power budget, do not have the memory or whatever. Yeah, your CNN does not fit on your target platform. Well, then you have to go back to the whiteboard. Yeah, you have to redo everything, and you iterate this whole process a number of times. So this is a very inefficient process. Yeah, but this is basically what is happening today mostly. Now, what we have been doing, for example, is look at the design process of these DNNs and already take into account the information of the target platform. So we built very abstract models of the target platform or platforms, and we take those to have a architecture-aware process in the design. Yeah, and let me zoom in on this particular box to give you a little bit more feeling what that means. Yeah, so this architecture-aware design of these neural networks. So what we have done is we have built a GA-based, so genetic algorithm-based engine, search engine, which is actually just a NAS, which is a network architecture search. But you can also see it as a design space exploration engine. So it has a population of different designs, DNN designs, and then it clearly evaluates these designs for multiple objectives. It evaluates it for memory, energy, and performance. Yeah. So, and this is of course related to the target platform that we will be mapping on. Yeah. And it will evaluate it according to the accuracy. Well, that's a problem because we all know that training takes a long time. So we cannot fully train all these networks during the search. So what we did is invent a new method which we call piecemeal training, where we basically train every model for a very short time on a very small fraction of the data set. But that gives us a feeling of how good these potential candidates are. Yeah? And those, given those results, we can do the genetic operations on these networks. So we make slight changes to these networks. And the best will survive of these networks. And then, so these partly trained networks will then, those that will survive, will then go into the next iteration, and they will get trained a little bit more. Yeah. So those networks that survive for a long time will get trained more and more and more. So that's what we call piecemeal training. And this works. Yeah. So we have shown that we can deliver pretty much state-of-the-art neural networks doing this. Yeah. Okay, so let me skip that one. So this is what you actually get. Yeah. So here you get actually not one neural network, but you get a selection of what we call Pareto optimal neural networks. Yeah, where you can, as a designer, you can select one of these, and you can find different trade-offs in terms of. This is for 3 data sets. You can trade off, for example, energy versus throughput and accuracy. Yeah? And dependent on the target platform or the requirements, you can select one of these neural networks. But you can actually do more. Because you have this set of different neural networks, you can actually use multiples of these neural networks to exploit them at runtime. Yeah. So we also worked on that. So you can, for example, you can imagine a system, let's say a drone, which has a power budget that changes over time. For example, it flies in bad weather, so it needs more power to be stable in the weather. Yeah, so it can spend less power on model inference. But in good weather, yeah, it can probably spend more power on model inference. So you can actually use a model that has a higher accuracy. Yeah. So what we did is we designed a kind of methodology to, in a very fast way, to change between these neural networks that are running on such a embedded system. And we do that in an efficient way, such there is, for example, overlap between these neural networks. So if you switch between them, yeah, there's kind of an overlap. It's kind of a pipeline type of execution. And also we looked into the memory consumption, yeah, because if you have multiple of these neural networks on the device, clearly that's not good for memory consumption. So we try to reuse certain layers in these neural networks in order to optimize for memory consumption. And by doing that, clearly you can really adapt to let's say, changes in the physical environment. Yeah, by changing also the neural network that is running on your system. Now, still, if you look at these methods, doing edge AI is still very much challenging, and the reason is that if you want to fit very large neural networks on your edge device, you still run into the problem it's not going to fit. Yeah, so there are a couple of solutions to that. Clearly, compression. A lot of people are doing research in compression of these models, but this may be at the cost of a loss of accuracy. Yeah, and then there's a lot of people that are doing research on what we call this vertical splitting of neural networks. So a part of the neural network is being executed on the edge device, while another part is executed upstream towards the edge. Yeah, so you vertically, let's say, split your neural network within the edge to cloud continuum. Well, that's possible, but then you still have this latency problem, and you still have this problem of privacy. Yeah. So in our group, then we are looking at a third solution, where we actually try to exploit the resources we have in multiple edge devices. So instead of doing vertical distribution, we do a horizontal distribution of these large neural networks. So the idea is actually shown over here. Yeah, so here you try to split up this neural network and divide it over multiple edge devices. Well, this is all technically possible right now, but it still requires a lot of manual effort to do this. Yeah, a lot of programming effort, a lot of parallel and distributed computing and programming effort. So it's not easy to do this. So that's why we built this environment very recently, I must say, which actually automates this whole process. Yeah. So what it does, it takes a CNN in this case as input, and it automatically splits this CNN over multiple devices. Yeah, it produces the code and deploys the binaries to all these devices, such that they can actually work together in a distributed fashion. And for that, we use the well-known Open MPI standard to actually have the different devices communicate and synchronize with each other. Yeah? But also, we exploit the fact that some of these devices have internally multiple resources, like a multi-core or a GPU. So internal in the device, we can also exploit parallelism. Yeah, so we can actually map different layers to the different resources. And for that, we use the OpenNP there. And this is all fully automated. So let me just show you how this works. And this is a very busy slide, so I'll talk you through it step by step. Yeah, so don't worry. On the left side, there are the 3 input specifications that are required. Yeah. So first of all, there's this platform description that describes the target platform. So which edge devices do we have? Yeah. What kind of resources do they have? Do they have a GPU? What type of libraries are running on it, and so on. So this is the target platform specification. Next, we have the CNN. And we use the well-known ONNX standard for that. Yeah, so we can actually use any ONNX defined neural network there. And there are plenty of them out there. Yeah. And then third, but very important, we have a mapping specification that tells you how the different parts of the neural network, for example, how the different layers of the neural network are being mapped to the different resources. Yeah, that could be the different edge devices, but that could also be the different resources within an edge device. Now, given these specifications, these are the inputs, the system automatically generates an intermediate representation. And this intermediate representation consists of the different submodels that should run on the various edge devices, together with a communication recipe, that specifies how these different submodels should talk to each other. So how they should communicate and synchronize with each other. And given that intermediate representation, we can actually generate automatically again the code for it. For every edge device, the code is generated that uses this MPI, OpenNP, and so on to exploit all the parallel resources that are out there. Well, doing that, you can very quickly realize various different distributions. And again, you have different trade-offs there. So you can have distributions that are good for throughput, that are good for per device memory footprint, or per device energy consumption, and so on. So you can give the designer a lot of different trade-offs there, in a very quick way. But it can also help you in improving, for example, the memory footprint. So if you distribute a very large CNN over multiple edge devices, it's clear that the per device memory footprint is much smaller than if you would run the big CNN on a single edge device. And the same is true for energy consumption. And in some cases, we can even also improve the throughput of the system. But that really depends on the type of communication system, for example, you use between the edge devices. Right. Okay, so that's, I think I'm still on time here. So I still have a couple of slides, if I may. So let me use the remainder of my talk to say a little bit about what AI can do for our systems community. So I'll give you one example of a project that we're doing together with a big company in the Netherlands, ASML. You might have heard of it. So this is the market leader in making chip lithography machines. So these are basically the chip printers. They print basically chips. And these are very complicated machines. So these are distributed machines having over hundreds of cores, having over multiple hundreds of software processes running on them. Now, sometimes they have a problem where they have, let's say, they encounter performance issues on these machines. We call those performance anomalies. And there are all kinds of reasons for that. And one of the reasons is that customers like Intel just add software to these machines, which was not really expected at design time of these machines. Now, so what we try to do here is to use AI and AI methods to try to help the operators of these machines to detect and, if possible, also identify the type of performance anomaly. So because of the time, I will, okay, let me spend a few seconds on this slide. So what we exploit over here is the fact that these industrial embedded systems are highly repetitive. So that's a good thing for us. And of course, they are very data rich. So they produce a lot of data, so we can monitor these systems. So we can monitor what's going on. So let me immediately go to the more detailed slide in order to wrap it up. So what we actually do is we monitor the system for extra functional behavior aspects. So this could be, for example, the latency of software processes, or the memory footprint of software processes, or the communication details of software processes. How many bytes or packets are they sending out per second, and things like that. So these are this is the extra functional behavior we try to track per process in these machines. And actually, we try to do it on an even finer grain, because within the processes we also identify certain phases. Yeah, so because the execution in these kind of machines can have different phases with really different behavior. Yeah, so we actually try to capture the behavior within these phases. And what we do there is we then create what we call software passports. And this is basically describing the reference behavior. So how the behavior should be of these phases and these processes. And what we can actually do then is do the same trick, but then at runtime. Yeah, so and then we don't call them passports, but we call them signatures. So that is the behavior that we actually measure at runtime in the system. And then we can actually compare the two. Yeah. Is the runtime behavior, is it close to the reference behavior that is being specified in these passports? And if not, yeah, clearly we have some type of anomaly. Now, if it is possible to have some examples of these type of anomalies, we can also try to actually identify. Yeah? And we have done so in an experiment where we had a digital twin, for example, of the system, and we could inject some different types of timing anomalies, and we actually applied some very classical machine learning techniques. So no fancy deep learning here, although we also looked at that, but very classical machine learning. And what we can see is that we can already achieve a very high, let's say, accuracy for in this case tree-based algorithms that can already identify, let's say, the type of anomaly that is happening in the system. And clearly this could help, again, these operators to quickly find and resolve the issues. And with that, let me wrap off and thank you all for your time.